Very good morning. Welcome to the course on Smart Grid, Basics to Advanced Technologies, and we are going to discuss on battery management system today. The main functions of battery management system, that is so called BMS, are monitoring the current through the circuit, cell voltages and ambient temperature, estimation of key states such as SOC, SOH and SOP using online estimation techniques. Cell balancing to balance the voltage or SOCs using active or passive components. Computing the energy and power limitation of the pack using estimated SOC and SOH values. However, in this lecture, our contributions are confined to the demonstration of cell balancing techniques only. A detailed description of other functions is provided in the previous BMS lecture. Generally, the health of the lithium ion batteries will be degraded after some cycles of usage. This poses differences in their capacity and results in a decrease in their efficiency. The weak cell in the module charges and discharges faster compared to other cells. To mitigate these issues, balancing of cells are necessary and it allows the batteries to look alike in capacities and increase the efficiency of the cells in a given module. Cell imbalance can be categorized majorly in two types. First one temporary and the second one is permanent. The temporary causes of cell imbalance include uneven distribution of leakage and self discharge currents. The difference in Coulombic efficiency, which is a minor imbalance, performance or operation and uneven temperature distribution. Assuming that all the cells have the same composition, the Coulombic efficiency, performance or operation and self discharge will be the same, leaving the most significant imbalance factor, uneven temperature distribution and leakage currents, current distributed to the BMS. The permanent causes of cell imbalance include internal resistance change, self discharge rate, damage to static electrolyte interface and capacity differences. If this continues, the weak capacity cell will gradually deteriorate prematurely than others. Imagine a case where a less capacity cell and fully capacity cell are connected to a load, it will neither discharge nor charge. A detailed discussion on the importance of requiring a balancing circuit in the BMS is provided in the theoretical lecture on the BMS, that is battery management system. Kindly refer to the lecture for more detailed information. There are many cell balancing methods. Cell balancing is broadly divided into two methods, passive and active methods. The passive methods are segmented into overcharge and shunt resistor methods. The active balancing methods are segmented into cell to cell, cell bypass and pack to pack balancing. The basic balancing required for a module is cell to cell balancing, also called cell balancer. This cell balancing is again subdivided into adjacent cell to cell, any cell to any cell and direct cell to cell balancing. Let us consider the passive balancing system. This experiment aims to demonstrate a simple passive balancing for the charging and discharging operation of 3 lithium ion batteries through a readily available balancer IC. The bleeding resistor present in the ICs allows the charge of the higher capacity cell to deplete through this resistor for both charging and discharging operations. The components required for this experiment are 3 18650 lithium ion cells, a readily available passive balancer IC, a DC power supply for charging operation, a rheostat for discharging operation. Let us get into the component specifications and their importance in this experiment. 3 18650 lithium ion cells of 3000 milliampere hour capacity with a nominal voltage of 3.7 volt each are used in this experimentation. The lithium ion cells are connected in series combination to make up to 11.1 volt. The passive balancer IC with specifications as 3S 20 ampere and 12.6 volt maximum, it can handle 20 ampere of current and have protection for short circuit, overload, discharge and overcharge, which provide safety and protection for the lithium ion batteries. A DC power supply is used to charge the battery and a rheostat of 20 ohms for discharging operations. You can see the passive balancer IC. The connection diagram consists of 3 positive connections from the battery and 1 negative terminal connection, and a pair of positive and negative is provided for the external connection, which is for the charging and discharging connections. Now, the detailed architecture of passive cell balancing has been presented before you. This is the schematic of the balancer IC, which consists of 4 N channel 85N3L switching MOSFETs, DW01 overcharging and over discharging protection IC, G1 SMD NPN high voltage transistors, 2L PNP high voltage transistor, 1 port charging and discharging terminal and few resistors and capacitors. After connecting the batteries to the balancer IC, we are going to check the balancing operation for both charging and discharging using the DC power supply and rheostat respectively. Let us observe charging operation. The battery module is charged by the DC power supply and the path of the charging goes through the DW01 protection IC, and through that switching MOSFETs 1 and 2. Once the battery reaches its limit, the switching MOSFET activates and the current takes the resistive path until all the cells come to the same voltage. One of the threshold voltage or peak charge voltage 4.2 volt is reached, the protection IC activates and stop the charging operation of the battery module. Similarly, we can also see the discharging operation. In case of similar to the charging operation, the current passes through DW01 protection IC and through switching MOSFETs 3 and 4. Once the battery module reaches the cutoff voltage of 2.4 volt, the switching MOSFET activates and depletes the charge of other batteries until all the cells reach cutoff voltages. Similar to the charging operation, the DW01 activates once all the cells voltages reaches cutoff voltages. As we can see from the DC power supply display panel, we can see that 12.6 volt is appearing across the terminals of the balancer IC. With a current of 1 ampere and a wattage of 12.6 watt of power is storing in the batteries. Since the battery current takes the resistive path for balancing, heat is generated inside the module which leads to deterioration in the battery capacity and may even cause thermal runaway. In this regard, even though passive balancing is easy to implement and has less cost comparatively, it is not recommended for large modules because of frequent failures. Moving to active balancing, in this experiment we aim to demonstrate how an active balancing mechanism works by utilizing TMS 320 F28379D as a controller and Opel RT as a plant. To perform active balancing, one should determine 3 major factors: mode of charge distribution, for example, direct cell to cell, adjacent cell to cell, energy sharing, balancing topology, that is type of converter, boost, buck, flyback, half bridge, and third is balancing strategy, that is what type of control logic parameters need take care of, example voltage, OCV, SOC and SOH. Now, this is what generally the CHIL setup look like, and in due course of time I will be explaining you the complete operation of CHIL setup. Now, first of all, what is a CHIL experimentation? The controller hardware in the loop system allows the verification of the proposed control logic provided in a real time controller in conjugation with the plant which is running at a very fast time scale either in real hardware or controller. Thereby, any changes in the control logic in the real time should be governed and possessed by the fast acting plant. The components required for this experiment are a TMS 320F 28379D launch pad and an Opal RT controller and a simple PC. In this experimentation, the charge distribution considered here is energy sharing and balancing topology is a boost buck converter and the balancing strategy is based on SOC. This is the schematic of CHIL experimentation. The working of CHIL is shown in this diagram. Firstly, the TMS board is equipped with ADCs and EPWM pins. The input will be provided from the Opal RT which is taken here as a plan to the ADC of the TMS board and is utilized for the control logic development. By utilizing MATLAB, the control logic is developed and through hardware simulation, the developed code in MATLAB is flashed into the TMS board. The necessary parameters will be called out into the console to verify the control logic for various parameters. The EPWM terminal pins present in the TMS board generates PWM pulses which are connected to the Opal RT through digital input pins provided to it to drive the converters. Let us discuss the construction of CHIL setup in the following steps. Step number 1, consider a battery system of 3 modules so called plant in Opal RT. Step number 2, call out the necessary parameters required for balancing strategy from the plant. Step number 3, develop a balancing code in MATLAB using the called out battery system parameters. Step number 4, do the necessary connections, that is the parameters from the Opal RT analog out pins to ADCs of the TMS board with proper scaling. The PWM pulses from TMS board EPWM pins to digital out pins of Opal RT to drive the converter sitting in the plant. Now, you can look into the complete block diagram of the battery system within Opal RT. This is the block diagram of the battery storage system connected to a DC bus, and from the diagram we can observe that the 3 battery modules connected to a load or charger, each module consists of a CMB known as cell management block, which consists of cells connected in a series parallel combination with a balancer circuit. The driving circuit which takes input from TMS drives the MOSFETs. Let us discuss the working principle of the battery system. The system consists of 3 modules and a boost buck converter, each to step up or step down the battery voltages as per the requirement. Such a mechanism is called energy sharing because each module can be controlled individually, which resembles the sharing of the power demand accordingly. If the duty cycle D of all the converters are same, then all the batteries share power equally. By using this concept or mechanism, we have developed a control logic that provides duty cycle D based on the variations in SOC values of the battery system. A TMS board is equipped to generate the desired PWM signals. The TMS board, which takes the input from the OPLRT currents SOCs and power demand PD, generates D1, D2, D3 duty cycles based on the algorithm flashed into the microcontroller. The parameters of the storage system are presented in the table as shown. The initial SOCs are taken as SOC 1, which is 65%, SOC 2 62% and the SOC 3 70% respectively. The average SOC is close to 65.66. The nominal voltage for 3 modules is 48 volts. The capacity of modules is taken as 5 ampere hour each and initial DC voltage is 270 volts. Initial power demand is 1000 watts. The converter parameters as inductance of 5000 microhenries, the capacitance of 200 microfarads with switching frequency of 5 kilohertz. This is the back panel of OPLRT where we can see multiple groups. The group 1 consists of analog in and analog out. Group 2 consists of digital in and digital out. As we can see, for our experiment purpose, we have used 7 analog out signals with a ground pin and 3 digital in signals with a ground pin connected through a DB37 channel. After setting up the connections as per the block diagram, let us understand the simulation platform of both OPLRT and TMS board. Firstly, the required MATLAB installations for the TMS board need to be done. Also, the control suite for the C2000 microcontroller is required, which provides libraries at every stage of development and evaluation. After the installation, MATLAB provides hardware libraries for the TMS board. In this experimentation, we have taken 7 parameters as an output from OPLRT analog out for control algorithm. The parameters are input battery currents, SOCs of 3 batteries, also the power demand PD. All the 7 parameters are scaled down to 3 volt at OPLRT itself, because the TMS board runs on 3.3 volt only. Any higher voltage might damage the board. 7 ADC blocks are taken for the 7 input parameters. 3 battery currents are compared with reference currents generated from the algorithm. The SOC balancing algorithm is developed based on the average standard deviations. By comparing the SOC values with the mean values, a balancing factor is determined for all the 3 batteries in a similar way. Using the balancing factor, the power is shared among the battery module accordingly. By using a PI controller, the voltage bus is maintained and also develops PWM signals. These 3 signals are sent to the Opal RT through digital input pins for 3 converters presented in the plant. The Opal RT plant model, which consists of 3 battery modules and 3 converters that are connected to a common DC bus with a power demand of PD. Now, let us focus on its operation. To evaluate the proposed control algorithm, experimentation using a built-in MATLAB equivalent circuit model is developed. The simulated model consists of 3 battery modules and each module is connected to a bidirectional DC-DC boost buck converter for discharge and charge operation according to the reference current provided to it from the control algorithm. The converter consists of an inductor of 5000 microhenry and a filter capacitor of 200 microfarads. The battery nominal voltage taken here is 48 volt for each module. Now, if you focus on discharging operation, the individual battery currents is presented in the DSO at the first 3 channels and SOC values in the next 3 channels and power demand PD in the 7th channel respectively. Now, let us focus on the variations in load demand. To examine the control algorithm for load power variation, load power changes are applied to the batteries during discharging operation. Initially, the power demand is kept at 1000 watt and a gradual increase of power by 200 watt is applied till the power demand reaches 2000 watt. We can observe the input current of batteries in the first 3 channels of DSO. Also the SOC values are draining faster than the earlier. From this, we can understand that the algorithm takes the power demand changes without any setbacks. Variation in bus voltages. In general, the DC bus voltage from the energy storage should be always maintained irrespective of changes in battery voltages. Let us observe how the V bus changes are taken care by the proposed control algorithms. The initial DC bus voltage is taken as 270 volt and then it is changed to 300 volt and 260 volt respectively. It can be observed from the DSO the change in DC bus voltage does not affect the battery voltages or currents and the DC bus is perfectly regulated. Variation in SOC values. Let us change the SOC values to 75, 73 and 65 respectively compared to the previous values for all the 3 modules and observe its effect. From the DSO, we can observe that the change in SOC is proportional to the currents of the battery, which validates that the proposed algorithm is working exceptionally well to cater to all the changes. In this lecture, we have learned the two popular balancing techniques, that is passive and active balancing, how to develop a control logic using a low cost TMS board, understanding of how to develop and work on a CHIL setup for a balancing mechanism. I hope and confident that this lecture drives you to work and develop balancing mechanism for various topologies and balancing strategies of batteries in future. Thank you.